Morning, sir. My name is Yel Monica, and I am currently studying BTech second year ECE branch at SRIT College. Today, I will be presenting on the topic of procedure to construct root locus under the subject control systems. Introduction to root locus. Definition. The root locus technique was introduced by W.R. Evans in 1948. It is a graphical method used to analyze and design control system. It illustrates how the roots of the characteristic equation change with varying gain, offering valuable insights into system behavior. Purpose of root locus. The primary purpose of the root locus is to predict the behavior of closed loop poles as the system parameters changes. This helps in designing stable and efficient control systems. Steps to construct root locus. First step is location of poles and zeros, and second step is root locus on real axis. Third step is identify angles of asymptote and centroid. Fourth step is breakaway and breaking points. Fifth step is angle of departure and angle of arrivals. And the sixth step is point of intersection of root locus with imaginary axis. And the seventh step is test point and root locus. In the process of constructing root locus, the first step is location of poles and zeros. Draw the real and imaginary axis on an ordinary graph sheet and choose same scale both on real and imaginary axis. To find poles and zeros, consider open loop transfer function. To get poles, equate denominator equals to 0. And to get zeros, equate numerator equals to 0. Then we get poles and zeros. The poles are marked by cross and zeros are marked by small circle. The number of root locus branches is equals to number of poles of open loop transfer function. The origin of a root locus is at a pole and the end is at a zero. Let n equals to number of poles, m equals to number of finite zeros. Now, m root locus branches ends at finite 0. The remaining n minus m root locus branches will end at zeros at infinity. And the second step is root locus on real axis. In order to determine the part of root locus on real axis, take a test point on real axis. If the total number of poles and zeros on real axis to the right of this test point is odd, then the test point is part of root locus. If it is even, then the test point does not lie on the root locus. Third step is angle of asymptotes and centroid. If n is number of poles and m is number of finite zeros, then n minus m root locus branches will terminate at 0 at infinity. These n minus m root locus branches will go along an asymptotic path and meets the asymptotes at infinite. Hence, number of asymptotes is equals to number of root locus branches going to infinite. The angle of asymptote and the centroids are given by the following formulae. Angles of asymptote equals to plus or minus 180 into 2q plus 1 divided by n minus m, where n equals to number of poles and m equals to number of zeros, where q equals to 0, 1, 2, 3 up to n minus m. Centroid equals centroid, meeting point of asymptote with real axis, that is equals to sum of poles minus sum of zeros divided by number of poles minus number of zeros. The fourth step is breakaway and break-in points. The breakaway or break-in points either lie on real axis or exist as complex conjugate pairs. If there is a root locus on real axis between two poles, then there exists a breakaway point. If there is a root locus on real axis between two zeros, then there exists a break-in point. If there is a root locus on real axis between poles and zeros, then there may be or may not be breakaway or breaking point. Let the characteristic equation be in the form Bs plus K A of S equals to 0, K equals to minus B of S divided by A of S. The breakaway and breaking point is given by the roots of the equation. dk by ds equals to 0. The roots of dk by ds equals to 0 are actual breakaway or breaking points. Provided for this value of root, the gain k should be positive and real. And the fifth step is angle of departure and angle of arrival. Angle of departure. Definition: the angle at which root locus branches leave a complex open loop pole. Formula for angle of departure: phi d equals to 180 degrees minus sum of poles minus sum of zeros, where sum of poles equals to sum of angles contributed by all other poles at the complex pole, and sum of zeros equals to sum of angles contributed by all zeros at the complex pole. Steps to calculate angle of departure: draw vector from all other poles and zeros to the complex pole of intersecting. Measure angles between these vectors and the positive real axis. Sum angles from poles and subtract sum from zeros. Apply the formula to determine phi d. Angle of arrival: the angle at which root locus branches arrive at a complex open loop 0. Formula to calculate angle of arrival: phi a equals to 180 degrees plus summation of poles minus summation of zeros, where sum of poles equals to sum of angles contributed by all poles at complex 0, and sum of phi zeros equals to sum of angles contributed by all other zeros at complex 0. Steps to calculate angle of arrival: draw vectors from all poles and other zeros to the target 0. Measure angle between these vectors and the positive real axis. Sum angles from poles and subtract sum from zeros. Apply the formula to determine phi a, angle of arrival. The sixth step is point of intersection of root locus with imaginary axis. The point where the root locus intersects the imaginary axis can be found by the following three methods. The first one is RH criteria, second one is trial and error approach, and third one is substituting S equals to j omega in the characteristic equation and separate the real and imaginary parts. Solve two equations for omega and k. The value of omega gives the point where the root locus crosses the imaginary axis. The value of k gives gain at the crossing point. Also, the value of k is the limiting value for stability of the system. And the final step is test point and root locus. Choose a test point using a protractor roughly. Estimate the angle of vector. Draw to this point and adjust the point to satisfy the angle criterion. Repeat the procedure for a few more test points. Sketch the root locus from the knowledge of typical sketches and the information obtained in the steps 1 to 6. Test point and root locus representation on graph sheet. In conclusion, the root locus is a powerful graphical tool for analyzing the stability and transient response of a closed loop feedback system as a system parameter. Typically, the gain k varies. This visualization provides critical insights into how changes in the gain k affect the system stability margins, damping ratio, and natural frequency, ultimately aiding in the design and compensation of control systems to meet desired performance specifications. Thank you.